That sounds good. Thank you. First of all, thank you very much for inviting us, IBM, to give this talk. You have decided to spend the next how many minutes with us, so we really appreciate it. My name is Seetharami. I am a distinguished engineer at IBM TJ Watson Research Center. I'm part of the quantum team. I'm the chief architect for classical systems co-design for quantum-centric supercomputing. While I talk here, this actually is the work of massive number of people. Some are on the call, Tony and Yoon and EK and so on. But there is a large group outside of this, and also some of our partners. So I want to acknowledge that. Pretty much most of what I will say will be in this paper. There is an archive link to it, so feel free to look through it. And there is a number of papers that I will reference as we go through. I do like to make this a little bit more interactive. So if there are questions, please do post them on the chat. Yoon will check them and let me know through Slack. So I will know eventually I'll be able to address them. And I will try to leave some time at the end for Q&A as well. Okay, so today I want to talk about a reference architecture for quantum-centric supercomputer. As a way of introduction, I want to tell a story actually. So as you guys know, I think this was Supercomputing 2024. Jay Gambetta gave a keynote where he basically said QPUs plus CPUs plus GPUs all working together is what we call quantum-centric supercomputing. And this is necessary to accelerate scientific discovery. And this is kind of a definition that he threw out. I'm going to leave it there. I'll come back to it hopefully at the end. But I want to tell a story from a GPU perspective, because I'm not a quantum person with my background. I'm coming more from classical computing. And so when you think of GPUs, frankly, there is actually no GPU-centric supercomputer that at least I know of. But in fact, there are GPU-centric supercomputers that ended up being in existence. So it started as a GPU, as a PCI card, and afterwards a bunch of GPUs put together into a server. We have done that with our Summit supercomputer. Subsequently, of course, the DGX versions came out. And then that became the foundation for a lot of the AI work. And that also resulted in a huge proprietary AI stack from NVIDIA, but also a lot of open source AI stack from PyTorch and VLLM and LLMD and so on and so forth. So a combination of the GPU systems, and when I say NVIDIA DGX, actually, I mean really the reference design of NVIDIA DGX, which is 8 GPUs in a box with a bunch of CPUs and memory and so on. And then subsequently, you see the same system designs from AMD and others coming out with that kind of architecture. So that kind of, I think you can reasonably say that's a GPU-centric supercomputer with the software stack and use cases. So what I'm trying to, and we have designed, I'm the chief architect for a number of systems we have built for AI called Vela and Vela 2, and now we are doing Vela 3 that are part of our IBM cloud, as well as we have deployed them on-prem systems. So I'm coming kind of from that background. So the existential question for more from a systems design architecture perspective is, what is a QPU-centric supercomputer and what does it look like? What's the software stack and so on? So that's kind of the fundamental question. I'll try to ponder through it. I'm not saying I have an entire answer, but we have collectively as an organization, we have a point of view. I'll try to share that point of view in this rest of the talk. I want to go to that with a little bit of a humbleness. So when I started actually working in AI back in 2019, 2020, we wanted to design a large-scale GPU cluster for our own internal use. And this is time before ChatGPT was a thing. So ChatGPT.com did not exist at that time. But obviously, we are coming from a long lineage of Watson AI system. So I worked with the AI researchers to actually extract information from them and as to what are the use cases for the system that they want me to build, a large-scale GPU system that they wanted us to build. And we looked at not a lot of things are important in this figure. The two parameters you want to keep in mind is the number of parameters, so that's the size of the AI model, and the type of input, output data, and intermediate data, so the number of tokens that they will be processing. And this is a survey I have done at that time. And this is the largest they thought we could go. And you could say IBM researchers are not creative enough, blah, blah, blah. But that's, all fair criticism, that they could conceive a multi-model 1 billion parameter model. This is something like projecting to 2024, 25, working on 40 billion tokens. And that may be about 4 terabytes of memory, and that needs about 1,250 GPUs for about 10 days. This is a 100 GPU era, obviously. That's kind of the largest. Remember, at that time, every word that you need, of course, somebody has to label it. There is no, label-based training and so on and so forth. So there is a number of limitations. But this is kind of the model that they thought they could go on. The models that they were training at that time were actually far smaller. There were something like 10 million parameters, 20 million parameters on maybe a billion tokens, maybe less than a billion tokens, things of that nature. But by looking at those use cases, they have provided us enough information to kind of design the system. So we have designed a system based on this, that we picked the 8 GPUs, and on the memory, there was a lot of questions. Why do you pick large memory? So GPUs had 80 gigabytes of memory. If you remember, A100s at that time came in 2 flavors, 40 gigabytes, 80 gigabytes. We put NVMe drives, and we put a bunch of other things. But basically that gave us directional guidance on what should be the node architecture, what should be the system architecture. And one of the things we have done in that system design is we said, we are not going to deploy InfiniBand-based system. We are actually going to do Ethernet with RDMA or converged Ethernet. And as you might imagine, certain vendor told us that's a bad idea, but now you can see a large number of AI systems are actually going in the Ethernet direction. And we have gone to that decision because by looking at the workloads, the projections, the kind of communication patterns that were needed, didn't really warrant this kind of a thing. And then the convergence between the Ethernet and InfiniBand, especially on the bandwidth side, made it very clear that Ethernet would be fine. And so that gives us a much bigger option of, network switches and racks and system design and so on. That also helped us, do we deploy this in cloud? Do we deploy this in on-prem? What are the requirements for it? Multi-tenancy requirements and so on and so forth. And subsequently, we use that to actually then say, it's not only a training system, because the minute these AI researchers train their models, immediately they're going to say, we want to deploy them for inference and getting customer feedback and so on. So that helped us to design system software stack. We use Kubernetes as our standard platform. We do training on it. We do tuning, inference, and so on and so forth. I tell this story to say, just having an initial collection of workloads, they may be right, they may be directionally correct, but not necessarily exactly represented. That is enormously helpful for system design and software design. So I'm going to spend a lot of time actually going over some of those workloads that we see. But okay, so now you can say, how accurate are these workloads? Actually, if you look at the numbers, apologies for the question marks, actually we were off significantly. By the time the system was designed and operational, actually the first month into the system operation, we were training these kinds of models that required going from a 1 billion max to 20 billion parameter models up to 70 billion. We were doing multiple trillion tokens. Right now we do 15 trillion tokens actually on these systems. So how far we are off is about 5 orders of magnitude. The workloads that we thought we will be running by forward projecting substantially and designing a system to the workloads that we actually ran is about 5 orders of magnitude. Software stack is different, bunch of other things are different. I'm just trying to make a meta point that the workloads that we will see probably are just exemplars, and they may be substantially off from where we need to get to, but they preserve the characteristics and the tenor of the communication patterns and so on, but we may be off. So I just want to humble myself by saying that. So the use cases I will talk about next might be just exemplars. We may be significantly off from where we are to next 4 years. Okay, so just keep that in mind. All right, if there are no burning questions, then I will move on to my reference architecture. So I want to talk to you about 6 different use cases. Actually, the paper has 5. We just added a 6th one coming out of our Think conference. I'll show you the one reference architecture picture, and I will also show like the 3-phase deployments that we envision. All right, no questions? Okay. All right. So on the reference architecture, so I'm going to give a little bit of a terminology, because a lot of times these are kind of positioned as either or. You need tight coupling, you need loose coupling, you need spatial coupling, you don't need spatial coupling, these kinds of things. And the view we have is a much more nuanced view on that. So I'll just give, of course, everybody knows what real time is, but I will say concretely it's between 1 and 5 microseconds whenever classical and quantum needs to interact at that kind of time scale is what I'm going to define as real time. Near time, maybe tens of microseconds to a second. This is both communication time, and some of it may include actually computation itself. And when I say batch time, that simply means each of the quantum and classical processors might be running for seconds to minutes to hours, and then they will initiate a communication, and that communication might result in longer time, not necessarily because the wire speeds, but more because of organizational structure. Your quantum system may be under a batch queue, your classical system is under a different batch queue, and those queues are not synchronized. So the job just goes and joins a queue and then it'll execute. So that may result in actually the longer time. Okay. I'll use two terms. Temporal coupling simply means the degree of time-dependent coordination. So that is, once I execute something on at time x, if I can execute at x plus delta, then I have strong or tight temporal coupling. So coordination in real time on near time windows. And if I say it's weak coupling or loose coupling in temporal domain, that means it's batch time execution. So I execute something at x and I put it in the queue, and the other side will execute whenever. Right? And temporal coupling you can achieve, of course, easily if you have physical collocation, but also so organizational policies enable you to achieve temporal coupling. Spatial coupling is the degree of physical proximity, that is strong or tight coupling is collocation, and weak or loose coupling is simply geographically distributed coupling between the two resources. Okay, sorry, that should be 6. Let me talk about the 6 use cases. So the first one, I think you guys probably heard many times from us, is finding the ground state energies of these molecules. There is an exact way to solve this problem called full CI or full configuration interaction. The challenge is, of course, the number of orbitals to the number of electrons spin up and spin down, and that's the product of the two. So it's combinatorial. But our team, again, I'm not necessarily the guy that's part of came up with this algorithm, but a number of members of the team came up with this method of extracting samples from a quantum computer and then using classical computer to diagonalize these samples to compute these ground state energies. The first use case is this model where we do some classical pre-processing on a classical supercomputer. We go to the quantum system, take the samples, and then go to the classical system, post-process them. There is, because in this particular use case, there is actually a way to do some error mitigation and try to improve the energies that you get out of this kind of a system. So there is a loop that goes on here. So it's a one shot. You go classical, quantum, classical, and you're done. So this is what we call open loop execution. A lot of our use cases, a lot of our clients actually use this model where they use our IBM Quantum in the cloud. And sometimes they have their own on-prem HPC systems or their laptops or whatnot. They use the quantum system, they get the samples, and then they post-process and pre-process on the resources that they have. A number of use cases fall in this kind of category. This is good for exploration. Right? In this use case, if you were to say what type of integration is needed, I mean, this is very easy to see. It's, exemplify batch time integration with loose coupling between quantum and classical systems. They don't really require any spatial or temporal collocation. Very easy to see, right? And so cloud-based deployment of quantum and distributed, HPC infrastructure is just sufficient. But as we started to do this work more closely with our partners at Recon and in other scenarios, what we have found is actually if you can do this in a loop, that is, you go to the quantum system, you get some samples, you go to the classical system, you post-process, but actually you can use that result to go back to the quantum system to get more samples. And if you do this in a loop, you can actually achieve substantially better ground state energies. And this is example where we have used the our quantum system at Recon as well as the Fugaku supercomputer, right? And you will see 2 dimensions. One is as you increase the subspace size, we get actually better energies. But as you increase the subspace size, you also need more classical compute so that you can achieve a reasonable execution times. 10 power 10 needs 152,000, which is the full Fugaku system, just to get the samples in 15 to 20 minutes, which is approximately the time it takes to actually get those samples from the quantum system as well. And there is a paper with more details on this. But and this is actually the time where we started to engage more. The HPC team started to engage, and when you look at them kind of classical compute resources for these kinds of use cases, you will see we are getting bigger and bigger and bigger. And if the only way a quantum system result can be used is with a Recon supercomputer, I think we are dead in the water, right? So not many people have these kinds of supercomputers. So we started to ask the question, is this the best way, or are there ways to actually optimize the performance? And vast majority of supercomputers are built with GPUs. So we started to actually look at what if we were to run this code. Again, keep in mind the diagonalization code is actually brand new HPC code. I mean, it uses the fundamental building blocks of a lot of BLAST library and so on and so forth. But the actual computation is fairly new, and it has to be written. On the Fugaku case, it has to be written with multi-dimensional parallelism so that you use the large number of fairly weak cores and small amount of memory very efficiently. So it's a new HPC code. I don't want to call it an existing HPC code that you just take and tune. It's a new implementation, basically. And so when we took that and ran it on a GPUs, but not necessarily ran it, actually re-architect the entire thing. So port it to GPUs first of all, and then optimize it by changing the array structures and so on. We were able to get substantial speed up, so close to 100x on just a node by node basis. So if you take a single node of CPUs and the GPUs in that node in Frontier supercomputer, we are close to 100x. In fact, we took that code and then it's actually enabled through OpenMP parallelization strategy, device offload. So we ran it on multiple different GPU configuration, MI250X, A100, MI300X, H100, MI355X, which is the AMD one that's coming up, and GB200. All of them are even higher speed ups. This is all to say that part of this quantum classical optimization loop, there is a substantial amount of work you have to do on optimizing the classical code. Now, the question is GPU the best device for this kind of workload? Based on everything I've seen, while GPUs achieve substantial speedups, it's actually a terrible device. I would say it's the worst device we have for this workload. I'm gonna leave it there. We can have a discussion later on. Okay. So what can we do if we have that kind of a GPU acceleration? We achieved 150x improvement. We are able to actually do even a larger subspace problem, 10 power 11. The previous number was 10 power 10, and we are able to improve the energy by another 29 millihartly. Apparently, in the chemistry world, this is actually, again, changing a huge amount of improvement. We are still not exactly at the chemical accuracy or the accuracy of classical methods like DMRG, but a substantial improvement over this. And all we needed to do was actually 784 GPUs for about 10 hours to do this whole loop, right? So this enabled us to be able to do these kinds of large diagonalizations very efficiently using GPUs. And that's what actually feeds into the next process. So in the closed loop calculation, I know there is a handout I'll get to in 1 minute. We actually do this optimization in a more closed loop manner where quantum samples are obtained, and then the classical processing happens on Fugaku, and then you get back, but you actually do this in an iterative fashion. And the way to do this is actually going and reserving both quantum and classical systems, and this becomes an important point we'll touch on a bit later. But what you see in this manner, so if you want to get to not just run once, go to the quantum, run once. Yeah, I'll answer the question in 1 second, if you don't mind. I'll finish this and I'll answer, okay? The closed loop model requires availability of both quantum and classical systems in a timely fashion. So I can run on the quantum, go to the classical, do this diagonalization, and use that information to come back. And so I can produce a plot like this in a reasonable amount of time. Let me pause here, take a breather, and answer the question. Please go ahead.
Hi, so could you go to that slide with the 10 or 12 iterations and explain a little bit more? It was the one with the 12 iterations and what was done in there, right? So over here.
Which one is this one? This one?
Yeah, let's start here and the next one. I'm trying to kind of follow along, right? So someone took a lot of effort to take something that was running on a supercomputer with CPUs to sort of use OpenMP to put things on GPUs and with some sort of a benefit, right? So 2 to 3x. Okay, and a lot of manual effort, and
it's more like 100x just from a CPU
over
to
here.
GPU.
Okay, all right.
And then under additional 3x, this is 1x is MI250x, and then use other GPUs to get even.
Okay,
like 300.
Sorry, the graphs and the labels went too fast. So okay, so now I understand. Yeah. So the high level bit is if someone goes through the effort and multi-months or whatever, multi weeks to go something with the open MP targeting GPU and figuring out how to do algorithms and sort of all the stuff in there. Great, you get 100x, and there's a variability depending on the architecture and the of the GPU complex. If you go through the iterations, I think that was the next graph.
Yeah.
This one. So this is 10 to 12 iterations in that closed loop, or how should I understand this, and what are the axes? What is the y-axis, and
So
talk a little bit more about this.
Right. So this is the energy in in hartrees. Lower is better, right? And this is I just put the dot here. Actually, it's multiple iterations just to show the GPU number kind of falls somewhere in the red dot here. Basically, it's about 29 millihartree. This is millihartree. These are hartrees. So 29 millihartree below the best number we could get on the Recon supercomputer.
Okay, and roughly speaking, an iteration was 10 hours. If I look at the fourth bullet.
Yeah.
Sorry, I'm this is second nature to you. I'm trying to kind of follow. So
that's correct.
Okay,
that's correct.
Right. Yes. Okay. So I think I'm oriented. Thank you for explaining some of these. Yeah. Okay. Thanks.
Absolutely. And so what this enabled is actually a more recent experiment we have done with our partners at both Recon and Cleveland Clinic, where now we are able to handle much bigger systems, chemical systems, where we can take multiple atoms, we can fragment that kind of a system. And so that means you create multiple fragments, and then you execute these fragments again through the same process: classical pre-processing, quantum sampling, and then classical post-processing. But at the end, you take all those results and then you recombine them to see what is the ground state energy of the full system. That's much, much bigger than any single quantum computer can handle. And this is a paper we just put out actually the other day. And in this case, we are able to use 2 supercomputers and 2 quantum computers in parallel because the number of fragments here are really large. So here is kind of a roadmap of how this SQD kind of use case has evolved. We have started with this open loop. That's what I described, where we used a single problem system, a chemical system. This is Fe4S4, number of QPUs, 1 QPU, 1 supercomputer, some amount of time, you get this kind of result. And then you go to the closed loop where you're able to improve that performance. And then we started to introduce this parallelism, because now we can do this fragmentation that I described in the previous page, where we take much bigger molecules. In this case, we had 300 different fragments, and each one of these is like this. And you're able to then compute both quantum, get the quantum samples and the classical, and combine the result. And the more recent one, we're able to get to 12,000 atoms. And so these are literally 12,000 individual fragments that you're actually processing, basically applying this methodology. But here, since you have so many more samples to capture, we actually use 2 different quantum processors, 2 different supercomputers. One is the Recon Fugaku, the other one is Miyabi G, which is a GPU-based system, where we use a substantial amount of CPU time on the GPU time to get these results. And if you forward project, it's easy for anybody to see the direction it's going. So we'll be able to do more and more of these. So that means we can address chemical systems that are much larger than at some point classical will not be able to keep up, right? So I give this collection of 3 use cases kind of as exemplars of the kind of quantum classical interplay that we see in application space. Okay. Beyond the applications, there are 2 more use cases I'll quickly touch on, actually 3 use cases. One is in the error mitigation domain. In error mitigation, there is, when you have large circuits, there is ways you can use classical computing, HPC, to perform a number of different type of operations and then use that learned noise model on quantum computers to actually generate results that may be more accurate than actually pure quantum only. And in those methods, we are again prototyping these workloads as we speak. These techniques really require much more tightly coordinated execution between quantum and classical. I'll leave it there on that front. And the next 2 are more in the fault-tolerant quantum computing domain, where real-time decoders, so the general characteristics of real-time decoders are you get the syndrome data, these are called the detectors, and then you have a decoder that will actually say most likely errors and then correct for those errors. To run the real-time decoder, of course, you need a very high throughput, so that's about 1 syndrome cycle per microsecond. You need really low latency to get the best possible logical error rate, right? So we do 2 pieces of work in this space. The use case 5 is more of, actually I would call, outer code research for fault-tolerant quantum computing. So things like error detection in Clifford circuits using space-time checks. There is a paper from our colleagues that is doing this. This kind of quantum error detection research can be performed fairly with a logical processor, classical processors operating with the quantum execution over. We are still quantifying. When I say high bandwidth, I don't want to put a number yet because I don't have the number yet, but we think that substantial amount of bandwidth is necessary. This does not mean we need bandwidth above what AI systems are providing, not the 3.2 terabits kind of bandwidth, but more than a 110 gigabit kind of links. Okay. Next use case is more in the outer decoder for fault-tolerant error correction. Our team strongly believes that you could actually build hierarchical codes, and there is evidence in the community as well, where this kind of hierarchical codes can result in substantially lower logical error rate. And in order to support these kinds of hierarchical codes, you need an outer decoder, and this outer decoder is going to be operating on a system that already has an inner decoder, right? Like the QLD PC codes. We assume the inner decoder is part of the quantum system, but the outer decoder is something end users or customers would want to really experiment with. And there may be outer decoder that is more application specific as well. So for those kinds of use cases, we expect the interaction between the inner decoder and the outer decoder has to be on a reasonably low latency, which is kind of near time kind of latency. That's kind of the expectation we have. So this is kind of a graphical picture of the distinction between the outer decoder and the inner decoder. So again, inner decoder part of the quantum system, outer decoder could be a collection of GPUs, CPUs, maybe special purpose things that could be part of this outer decoder, maybe FPGAs, things like that. Okay, so let me put all of this in a single table so that we can actually classify them. The different use cases, I mentioned the 2 types of coupling: temporal coupling, so that means in time, what is the kind of coupling that's required across the use cases. I would say pretty much all 5 of them only require pretty much batch time execution. Maybe the error mitigation near time could benefit from near time coupling, but the QEC outer decoder R&D definitely benefits from the more near time. That's the temporal coupling, so that's time domain coupling. Spatial coupling, so that is in terms of space. I think it's loose coupling is fine for the first use case. The second and third primarily benefits from spatial coupling because spatial coupling also tells you that the quantum system and the supercomputer which are independently operated, but under the same organization allows you to do this kind of orchestration. So if we were to do this 12,000 atom computation without having dedicated access to the quantum and the supercomputer, that will take a long time. So that's why I call this co-scheduling required. So co-scheduling between quantum and classical for these kinds of use cases are required. And if we are going another factor of 10x or 100x, if you don't have co-scheduling, you'll never be able to complete that kind of task. Error mitigation, same thing, tight coupling, open loop, QEC, probably loose coupling is sufficient, but QEC outer decoder research, we think tight coupling is required. The other ones are not that important. So I'll say classical resources, HPC, GPUs, and so on. And the key requirements are listed here. Let me take a breather. If there is any quick question, I'll answer. Otherwise, I'll go to the next one. All right. Perfect. Oh, sorry.
Could I ask yes. Clarifying questions, right? So yeah. On the inner decoder, what is the bottleneck resource? Latency, bandwidth, CPU, a couple slides back, just kind of on the two more back, I think. Sorry.
Yeah, so this is the inner decoder.
No, if you go, yes. So I think, yes, somewhere you mentioned, is the bottleneck CPU, is the bottleneck latency or bandwidth for the inner?
So the inner decoder, I'll say it this way. We are doing a lot of work on designing and optimizing the inner decoder. I think actually the first challenge I believe is I think there is still a lot more work to be done in the algorithmic side on the inner decoder. The algorithms for inner decoders are not completely set. Yes, we have belief propagation, we have modified version of belief propagation with relay BP and so on and so forth. But for the kind of logical arrays that are required for logical qubits, there is, I think, more algorithmic work that has to be done. That's point number one. Point number two, with the given algorithmic innovations that are already there, implementation wise, it's actually not bandwidth, it's not compute capacity. It's really the memory access and coupled with compute capacity. So you need to be able to process these syndromes. So you see here there is a logical syndrome processing rate. You need to be able to process them fast enough that you don't create a backlog. The minute you have a backlog, then you are kind of dead in the water, right? And the algorithms are not deterministic, so they have long tails. And so any of these belief propagation algorithms and so on. So you need to be able to process even the worst case scenario under a certain tight time threshold. And in order to do that, you need the compute and memory. And when I say memory here, I really mean a lot of these algorithms just use SRAM. You cannot afford to go to HBM memory or DRAM or LPDDR or any of those. So having the right type of compute with the right type of and right capacity of SRAM memory is the biggest bottleneck in that space.
Yeah, thank you. This is very helpful, right? And so the analogy is like in compression, right? There's algorithms that have tails, or they don't have deterministic fixed number of cycles to operation. The same thing is in here, right? Depending on the error, quote unquote, right? The non-deterministic. Okay. Thank you.
Exactly. And since you cannot measure the direct qubit, you are asking, it's like something happened in your house, but police can only ask your neighbors what happened. And so, you have to go through this process, and sometimes you don't converge. Sometimes it takes longer to converge, right? So that's the challenge. Okay, hope that gives you an idea. All right.
Oh, very much so. Thank you.
Yeah. So and I put this slide because actually a lot of the times people, when they mean quantum plus HPC, they mean a lot of different systems. And from our perspective, I really believe that we are actually trying to build 3 different supercomputers at the same time with a quantum system. And you may think it's an exaggeration, but actually I strongly believe this. I think there is one supercomputer that all quantum providers are going to build part of their quantum system. That is what we call real time. So in order for QPUs and in order for QPUs to be able to become logical qubits and so on and so forth, there is a huge amount of classical computing that will be built, maybe with FPGAs, maybe with ASICs. And I mean, there is already a lot of FPGAs in a lot of our quantum systems for sure. There is more ASICs. Some of that work can be prototyped with GPUs, but at the end of the day, I think it's going to be a fairly custom processors, and those will be in hundreds of teraflops of compute that goes with every single quantum system with any large number of logical qubits. That is one supercomputer, and I think that supercomputer will be more of a real time in nature, and this will be something that every vendor is going to build themselves. So from a collaboration research opportunities perspective, I would think this collaboration here will be more in the fundamental algorithms exploration rather than actually co-designing the system itself. The other two, I think, is where there will be a significant opportunity on co-design. So that's real time. Laura, you have your hand up. You want to ask a question? Yes.
Yeah, please. So to the real time. So the real time is really about the health of the QPU of the quantum system. So this is the classical compute needed to keep the quantum system operational effectively.
Correct.
Right.
That's correct.
Yes. So I'm curious. So I'm really happy to see a number here because I've been really curious about this. The 1 to 100 teraflops. Can you discuss a little bit some of the reasoning that you're getting to that number? What size quantum system are we looking at? Kind of what is your thought about the 100 teraflops?
Yeah. So this I'm really thinking mapping it to our Starling kind of system configuration. I don't know what it will look for Blue Jay. Our Starling is the next quantum system in 2029 with the 200 logical qubits. I believe it's 100 million gate operations that we will be supporting. And in that kind of system configuration, again, we are, as I mentioned in the previous comment, we are still looking at the algorithm for quantum error correction, right, in the inner code. And I'm basically taking what we are seeing in these inner codes, a projection of the kind of computational resource you need when you put a collection of these modules together to deliver something like a Starling kind of configuration. So it's not one single device, but Starling is going to have, I don't know if it is public information, but there is a number of QPUs that will be put together. And each of those QPUs will have corresponding amount of classical compute. And I'm combining all of that to give this number.
Okay. And that 100 teraflops, I mean, that's fully dedicated. So because of the fully dedicated can do absolutely nothing else except keep that system going.
That's correct. Except keep that logical error rate to what we say is the logical error rate.
Okay.
And all of the operations associated with it. Right.
Okay, great. Thanks. And then can you talk a little bit more about the near time? Sorry.
So near time, this will be exposed through a single API. This is your quantum system API, right? Anything under this system will be exposed through an API, but outside of that API, you're going to be doing a lot of stuff. There is a lot of work to map your applications to these logical qubits. There is work while we will get logical qubits and error rates to certain numbers, but they won't be anything close to a classical 10 power minus 18 kind of error rate. So that means you still need error mitigation. I think people are going to continue to do error correction, both in exploring outer decoder algorithms and even exploring inner decoder algorithms, and transpiling these circuits actually to the underlying quantum system. So there is a lot of this kind of work that will happen in this near time kind of domain. I call this kind of maybe operations on a per shot basis or operations on a few shots basis. And that kind of system is going to be, again, classical operating system with GPUs, CPUs. Maybe this will be on-prem, so because the quantum system is on-prem, and that my projection is in the hundreds of petaflops of compute in the upper end, not necessarily the lower end. Again, existing classical systems are not necessarily the best for these workloads, so we have to figure out optimizations might enable us to get this number much lower, but we have to see. That's kind of where I put that number. And then the batch time is the work I just mentioned in all of our SQD optimizations, where you're using full Fugaku or 1,000 GPUs or 2,000 GPUs, whatever that number is. That I think is the kind of system that you could use kind of this exaflop compute. That will be a CPU, GPU, high performance networking kind of system. So I put that in the batch time case. I put the more closer one in the near time. and the other one, the real time. From an IBM perspective, we are working on all three of these, and I'll kind of give a sense for kind of where we are in the reference architecture. So let me just go through that right now. I'll skip this slide. I think many of you have seen it. These are kind of the different use cases. But let me, so from when we are thinking about a reference architecture, we are thinking about reference architecture that support all of these workflows. But as I mentioned in the beginning of my talk, in AI, we were 5 orders of magnitude off than what we thought would be happening. So that means it has to evolve with the capabilities of the system and the workloads, right? So what's our reference architecture? This is the overall picture of our reference architecture. I will try to build it in the next 5 minutes. So we say this is our quantum system. Our quantum system will be exposed through a quantum system API, or that's a single interface through which you interface with the quantum system. Today, a lot of them are, we have one QPU and a bunch of classical runtime, but as I mentioned, this is going to be scaling horizontally. So multiple QPUs, multiple classical systems, they're all connected over this real-time interconnect, doing all this error correction. And that is the interface through the quantum system API is the interface to access all of that capability, right? The next to that quantum system, we expect this kind of we call this a partner scale-up system. And the word partner is actually intentional. This is where we think we actually work with our partners like AMD and NVIDIA and others to design these systems that are co-located with our quantum system, but ideally over some kind of a low latency interconnect. Again, when I say low latency here, I don't really mean NVLink kind of low latency, some reasonable microsecond latency interconnect. That means our quantum system should have the right system stack as well as the classical system, so that you could have this kind of a low latency communication between the two. And importantly, it's co-located. We don't expect this to be a massive scale system, as I just mentioned, but reasonably sized system. We put scale up. I know in HPC we have a specific word for scale up. Increasingly, we see this as more homogeneous, maybe 8 GPU or maybe 72 GPU single system kind of thing, so that it becomes easy to manage, and also you can scale the workloads easily and so on. That's the only reason it's actually used as a scale up, right? Then outside of that, we expect this kind of a scale out system, which is, you can call your partner HPC GPU system or CPU system or some other accelerator kind of system that is connected to this complex over a high bandwidth. Again, high bandwidth here is not the HPC AI high bandwidth 3.2 terabits, but it's better than 1 gigabit or 10 gigabit. It will be somewhere in the 100, maybe 400, maybe 800, that kind of stuff, right? So that, but these are 3 distinct systems with different in the different domains. So we expect that interoperability of those systems is really critical. So that's the reason we call out for RoCE, RDMA, or converged Ethernet, ultra Ethernet kind of technologies. We don't know if UA-Link is necessary, but we keep that as an option. But interoperability, I think, is the key word here. That we need to be able to communicate across these systems. For workloads that actually couple across these systems, but for workloads where you process on one system and then you read the data later on, you also need a multi-tenant and multi-protocol, both file and object fabric, storage fabric. So we call that like the compute layer. The next layer, of course, I mean, if you want an HPC guy to program to each one of these things, is going to be a nightmare. So we expect a system management orchestration layer, pretty much existing system management orchestration layer, enhanced with many of our QRMI, our quantum resource management interface, that exposes our quantum systems through this interface, so that you can leverage that in your resource management or workflow management systems. We do, as many of you know, we do extend Slurm to support this. I want to make it very clear, the extensions we do to Slurm or other schedulers are kind of, you should view them as reference implementation. As I tell many people, resource management and scheduling is kind of religion for a lot of HPC data center people, and we don't want to go change them, but we want to provide reference implementation so that they will be able to implement their own extensions, either it's for grid engine or for Flux or for we do it for LSF and PBS and other kinds of things. Systems and workflow is all over the place. On top of that is the application middleware layer. Again, we don't want to rewrite all of the MPI libraries and SHMEM libraries and CUDA and so on and so forth. But as you just saw in use cases, we need to be able to optimize those codes, or else the classical resource requirements for these quantum workloads will be so large that the value proposition of quantum might not show up. So we need to be able to optimize them. So that means new code will be written, but leveraging, building on the shoulders of existing classical HPC. Same thing on the quantum side. There is a huge amount of work that happens on the Qiskit and quantum tooling. So the reference architecture purpose is to kind of provide an integration play between these environments. I know a lot of people talk about unified programming model and so on and so forth. We don't yet believe that we are at a point where we can actually prescribe a unified programming model. I think it comes down somewhere down the line. We don't know when. So I think we are going to carefully evolve this, and as use cases mature, then we can actually talk about the unified programming model. I'll just do a short pitch here and say, people often talk about scheduling. I've seen some of this actually discussed in SC and other places. I do believe coupled scheduling across quantum and classical resources is really important. As I just showed in some of the use cases, if you are doing 10,000 diagonalizations and getting samples 10,000 times or 100,000 times from the quantum system and running on QPUs, you need some kind of a coupled scheduling between quantum and HPC. HPC schedulers typically optimize for a single dominant resource. Now we have two dominant resources where HPC systems have their own queue, quantum systems have their own queue. But now we have this new third type of workload that requires access to both, or timely access to both of them. I think there is an interesting scheduling problem that has to be solved. And we are working on this, and we are happy to collaborate with people as well. I'll do a quick pitch for the QRMI, but you guys know that we have this quantum resource management interface. The idea is for us to expose our quantum system, but we want more people to expose their quantum system so that the layers above can build in a seamless way, so that we don't have to replace every one of these schedulers for every single quantum system. But that's a piece of work that you guys discuss here, so I won't spend a lot of time because I want to spend time on one more thing. This all, of course, get converged into this applications layer, or what we call classical libraries and quantum libraries, and they will be combined to generate, deliver these applications, because vast majority of scientists, just to be perfectly honest, don't care about the rest. They want their application. They need to be able to, they need to have easy enough tools to actually compose these applications and run them, rather than worry about the underlying infrastructure. And operationally, of course, our operational folks need software stack, system management, monitoring, and so on. These is topics that you guys discuss a lot, so I won't spend a lot of time, but that's an important aspect as well, as these quantum systems become part of a data center. All right. How do we envision all of this to come together? We don't actually expect all of this comes in a single shot, right? Just acknowledging this current state, honestly, quantum processors are really co-processors to HPC. They are usually in a corner somewhere in a suitable place, and HPC is there, and you saw a lot of the use cases. Just you run on quantum, you run on HPC, and you can do the orchestration. Over a period of time, we do anticipate more of a tighter coupling between these HPC and quantum, and some of this coupling is maybe in the time domain, so that is your scheduler and advanced middleware, and this interoperable fabric, so that you can transfer data, the near-time quantum error correction kind of research work that drives more of that middle tier that I talk about as scale up. And then further down the line in 2030 plus timeframe is where we think really a tightly integrated quantum and HPC, where even the HPC systems are not just existing CPUs, GPUs, accelerators, but actually they are co-designed to do the computations where quantum is not as good as. So you go to the quantum system and you might get some information, but then you go to the HPC that's tailored design to perform those operations very efficiently. As I just mentioned, for SQD, GPU is the best worst system, actually, right? And we are seeing the same thing in other use cases as well. So a unified programming model, maybe that is the right time. Interoperable high performance fabric. Of course, for these systems to be really operational, you need to support multi-tenancy and you need to be able to do some of this real-time QAC. So the deployment, we think, is kind of happens in a timely fashion in this way. So let me pause there. I hope I've given you enough information on kind of our point of view on quantum-centric supercomputing. Thank you. Happy to answer any questions. If I still kept you awake.
Excellent talk. Thank you. So I saw a couple hands come up and then go down earlier. So if somebody, Laura.
Yeah, hi, great. Really nice talk. Can you go back on your slides, kind of a little bit in the middle there where you had, just keep going for me, keep going, going. One more before you got to that, keep going. Sorry.
This has a lot of animation, so
Yeah. Okay. One more?
One more. Yeah, this one.
Okay, perfect. Yeah. All right. So here's my thing. With the co-location, I mean, what I'm starting to worry about is there's the ideal state of systems being co-located, right, for particular purposes. But there's going to be situations where I'm starting to wonder whether that's just simply not going to be the case for funding reasons, institutional, political reasons, what have you. So when I'm looking at things like, when I'm looking at like the real time, right, I think that it can be very easily argued and won that there's going to be classical compute that has to sit with the quantum compute for the health of the overall QPU system, right? I don't think anybody's going to argue with that. That's probably going to come part and parcel with the purchase of the quantum system, et cetera, right?
Yep.
Kind of accessory hardware. But then when we start to get to like the near time, right, and you've got error mitigation listed there, and what I'm wondering is the other components of this that you've got mentioned, so like the AI-based transpiler, the circuit optimization, that sort of thing. Do you envision that could live? Like, let's just imagine we've got a quantum system with its support classical compute in one institution, and many miles away, there's the supercomputing environment. Now, that near-time error mitigation can be put on to the HPC system at the supercomputing center. Or I guess what I'm asking is these assumptions of the on-prem, you kind of have infrastructure options, you have on-prem. That's assuming, it sounded like that was assuming that the HPC system was always with the quantum, and that on-prem is coming from the location of the quantum.
Not necessarily, sorry.
Okay.
So this is one location. This is in the same location or a different location. Let me just make that clear. I think these two are very clear. The middle one, I'm going to be very humble and say, we don't know yet. I really think we have to do a lot more experimentation and we have to mature the technology. And I think that will shake out. Some part of it may actually merge into the right and some part may merge into the left. Or it may become such that we actually have to have this and that will shake out. I really don't think, I'm least confident on the middle one.
Okay. No, see, that's exactly that. No, that's an excellent point. So I guess my overall wonder and concern is that exactly that middle ground. If you need information from the system in terms of the error assessment, mitigation, whatever, if that feeds into other components that you have listed there or otherwise. So is there an argumentation for that all to be together, like the points that you have there?
Right,
And if
right.
that's true, does that dictate where the systems have to be together, right? That's like the critical path. That's the sort of thing that I'm wondering about.
Right. Absolutely. We are going to work hard to really answer that question.
Okay.
But this is a kind of a starting point. I think this gives us enough flexibility and freedom to do the experimentation and then come to the right conclusions. Right.
Okay, right. Thank
Okay.
you.
Yeah, thank you.
Jeff?
Josh? Yeah.
Hi, yeah. Going back further, but we don't need to go into the slides. You were talking about building out the GPU-based HPC cluster and seeing 5 orders of magnitude difference between what you designed for versus what the workloads you were actually running were.
Yeah.
I just wanted to get some clarification if that was considered a success of like the designed architecture was actually able to support so much more than it was initially designed for, or was it an emergent property of just how fast the state of the art was moving there that you needed to actually adapt the design in order to accommodate the new capacity?
I would say it's kind of both. So when we designed these GPU clusters, we actually did not have RDMA. Looking at the workloads here, we did not enable RDMA. The systems were RDMA capable, but we did not enable because we couldn't do a business justification for enabling RDMA in a cloud has, as you might imagine, as expense, right? There is development work, there is prototyping, there is, other kinds of things that happen. We did not. But once we saw the direction, we were able to quickly go enable RDMA, and the same cluster, as I said, these clusters is exactly the same system. We were able to run these kinds of models. So in that sense, it's a success, but it is only a success because we actually thought this is going to be bigger than this, and we had enough flexibility that was built into the system. So when I am proposing this kind of a system architecture, we are taking a little bit of a forward pass, the leap, and saying, we think, today, if you have to say it, you don't need this, the middle one. You have the right and you have the left, and they can be wherever they want, and that may be sufficient. And I just showed you a case where we have to do 12,000 of these things. It's actually having them next to each other is beneficial. Not for latency bandwidth purposes, but more for organizational purposes, so that you can get allocation on both and do these kinds of experiments, right? But I'm saying having this actually gives us that flexibility, and depending on where these workloads shape up, it may end up being like that. It may end up being merged into the left or the right, or maybe it gets split and half goes into the left and half goes into the right.
Okay.
So hope that helps.
Yeah, no, that I think that's great. And it is always challenging to predict the future for system architecture, especially on multi-year timescales. So nice work.
Yeah, thank you.
So I see we're at the top of the hour. I had one question, but I'm going to let anybody else who has a chance, or if they need to drop, go. I also wanted to thank you for your talk today. I think it was fantastic and lots of good questions.
Yep, I'm happy to do. Thank you so much. Thanks everybody for your time.
Absolutely. So I will just forward my question on Slack if that's okay. Thank you.
Yeah, sure. I have a couple of minutes if you want to ask the question, I can answer so others can hear. Otherwise, yeah.
Sure. It was more to that last slide you had, the slide 31, where you had the middle column. It strikes me that some of these balances are very similar to our instrument scenarios, where we have, an instrument and our HPC, and we are trying to map where should we put co-located edge devices, if you will. It's very much aligned, I think, with this center piece, because your timing for the apparatus needs to be connected. So anyway, I'm just curious if you had any thoughts or things of that nature for these edge devices. Accommodating instrument workflows might come into play here as well.
Yeah, no, absolutely. Actually, it's really funny that you say that because we were having another discussion with another one of your colleagues from a national lab. And the discussion there was actually, should we treat our quantum computer as one of these high performance instruments, whether it's a beam, scanner or whatever. And there must be scheduling work that was done between HPC and those instruments. And is there any lessons we can learn from that to actually bring it to this co-scheduled HPC quantum model, right? I'm sure there is some classical computing that goes with it. That's the point you're making. Yes, absolutely. And I don't know enough actually. I would like to get more knowledge, more educated on these instruments and how people actually orchestrate them, and what kind of edge, infrastructure that might be going with them, things like that. Yeah, great
And
question.
I also think one other thing we can learn from that scenario is that the scheduling can feed back, because you may
Yes.
make decisions because a lot of those are allocated in advance. You might
Yeah,
have ways to choose sort of swapping somebody in and out, given they
yeah,
have a campaign for maybe a shorter period of priority. So
right.
it might
Right.
feed back as well for these co-scheduling scenarios. So thank you very
Yeah,
much.
yeah. No, absolutely. Thank you. Right.
All right.
Thanks, everyone.
Thanks,
Bye.
everybody.
Yeah,
Bye-bye.
bye.